So now that we understand what it means for a sequence to converge, let's come back to series. Because remember, if we had a series, we decided that to know what it adds up to, we need to think about the sequence of partial sums S sub n, which is the sum from k equals 1 to n of a sub k. So if this sequence of partial sums converges, so if this limit as n goes to infinity of S sub n, if that exists and is some finite number L, we say that this series converges, and we write that the series is equal to whatever that limit is. If the sequence of partial sums diverges to plus or minus infinity, then we say the series diverges to either plus or minus infinity, depending on which. And if this limit doesn't exist at all, then we say that the series diverges. So it is important to keep in mind that diverging to plus or minus infinity is just a special kind of diverging, right? So in the future, we'll have some facts about convergent series, and it's important to remember that to converge, a series can't go to infinity, even though it makes sense that the limit is, even though it makes sense to say that in this case a series adds up to infinity, this doesn't count as converging. Okay, in general, it's very difficult to tell what any given series is equal to, if it converges or not. So we'll spend some time coming up with ways to tell if a geometric series converges. And in general, it's easier to tell if it converges than to tell what it converges to. But there's one common case where we can figure out what a series converges to, and that's a geometric series. So let's look at a geometric series. So let's look at our geometric series sum from n equals 0 to infinity. Actually, I should put k's here so that we can write down our partial sums. Let's figure out, does this geometric series sum from k equals 0 to infinity of a times r to the k, does it converge, and if so, to what? So remember, this is the series a plus a times r plus a times r squared plus and so on. Now, when we talked about whether the geometric sequence converges, right, we figured out that it only converges if the absolute value of r is strictly less than 1, right? So probably we should only, if these individual terms aren't going to 0, they aren't going to add up to a finite number. So we should really only consider geometric series where the common ratio is between -1 and 1. Okay. So first, let's write down what is the nth partial sum, because that's what we're going to need to take the limit of. So that's going to be, right, sum from k equals 0 to n of a r to the k. And remember, that's a plus a times r plus a times r squared, and so on, all the way to a times r to the n. My n's and my r's look very similar. Sorry about that. Well, look, all of these terms have an a, so let's factor out the a. So this is a times 1 plus r squared, and so on. And you might have seen this before, but let's go through it again just to make sure that we know how it works. So this sum, it looks like a polynomial, and it has kind of a nice property, right? It has the nice property that if you multiply this by 1 minus r, let's just compute this. So you get first 1 times 1, so that's 1, plus, and then r times 1. So I'm distributing each term on the left over to this 1, and then afterwards I'll distribute it over to this minus r. So 1 times 1 is 1, r times 1 is r, and so on, all the way down to r to the n. And now let's distribute each term over here to this minus r. So 1 times minus r is minus r, and r times minus r is minus r squared, and so on, down to r to the n times minus r is minus r to the n plus 1. Okay, right before this, there's an r to the n minus 1 term, and when that distributes over to minus r, we get minus r to the n. Okay, and then when we add all these together, well, most of these cancel, right? All the stuff in the middle cancels. The stuff that doesn't cancel is 1 and minus r to the n plus 1. Okay, so what we've just seen is that 1 plus r squared and so on down to r to the n times 1 minus r is equal to 1 minus r to the n plus 1. But then if we divide both sides by 1 minus r, we get 1 plus r plus and so on down to r to the n equals 1 minus r to the n plus 1 over 1 minus r. Okay, well, remember this sum on the left here, this is the nth partial sum of our series, of our geometric, oh, almost, sorry, not quite. To turn this into the nth partial sum, I need to multiply both sides by a. So if we multiply this by a, that gives us our nth partial sum. Right? Our nth partial sum is a times 1 plus r plus and so on down to r to the n. And so this is equal to a times this messy fraction, 1 minus r to the n plus 1 over 1 minus r. Okay, so there's our nth partial sum. Notice that actually nothing we have done so far depends on r being between minus 1 and 1. Okay, so now that we have this nth partial sum, remember the reason we computed this is because the sum of our geometric series, the entire series, so a times r to the k, is going to be equal to the limit as n goes to infinity of this partial sum, if this limit exists. Okay, but now we know what this partial sum is. This partial sum is a times 1 minus r to the n plus 1 over 1 minus r. Okay. So let's see, this a is a constant multiple, so we can move that outside of our limit. Let's do that. And now we have to think about what is happening in this limit. Well, it depends on r, right? If the absolute value of r is bigger than 1, then this piece right here is blowing up to infinity if r is positive, or alternating between negative and positive very large if r is negative. And so in either case, the limit doesn't exist, although it might be positive infinity. But anyway, it's not finite. So the case we care about is when the absolute value of r is less than 1. So if the absolute value of r is less than 1, then we can continue our calculation here. So this is a, and now we can use all of the limit laws to move our limit over to this spot, right? This is the only spot that depends on n. So we can turn this into 1 minus the limit as n goes to infinity of r to the n plus 1 over 1 minus r. But since the absolute value of r is less than 1, when we raise r to very large powers, right, it gets very tiny. So this piece evaporates away to 0, and we're left with 1 over 1 minus r. Okay, so we get a over 1 minus r. And remember, what this is the limit of the partial sums, but that's the value of a geometric series. So what we have here is a value for any geometric series where the common ratio is between minus 1 and 1. So you can see that computing the value of a series is, in general, very difficult, and also depends a lot on what exactly the series is, right? These tricks that we used for the geometric series, we aren't likely to be able to use these particular tricks for many other kinds of series. So this is one reason that working with series is generally kind of difficult.